kick off. The title of this webinar is, What's the F with File Formats? So let's start with the F in file formats. What's the F stand for? It could be function. What is the function of all those file formats we have in the media industry? It could be fun. Well, it could be. You've got to be optimistic. It could be the frame rate. Do you know how many file formats don't tell you what the frame rate is? You just have to assume or guess. Again, what's the function of those file formats? We know what the name of the file format is, but what's it meant to do? What's the 4CC code of those file formats? And we'll look at where 4CC codes came from later. What are the features of those file formats? Are they really all different? Do they all have unique and distinguishing features that justify their existence? What's the history of those file formats? And we're going to look quite a lot at the history, because my personal belief is that with the rollout of ultra-high definition, high dynamic range, wide color gamut, and IP streaming, we run the risk of going back to the 1990s wild west of file formats just through accident rather than by design. What's the foundation of those formats? Who owns them? Where do they come from? And what's the future of those formats? And that's really the last little bit that I'll end with at about 10 to the hour. So why am I speaking? Well, I believe in educating. I believe that if you understand history, then you probably stand a good chance of having a good future. And this presentation really is all about the journey to today's file formats and what the future may hold. And I wrote that book. It's a big book, it's a thick book, and it really needs updating based on where the future is going, but more of that later. So today's topics, we'll start looking at the history, hardware, hard designs, hope and horror of where we've come from. We look individually at audio, video, wrappers, and caption files. It's MXF's 10th, or maybe 11th, or maybe 12th birthday, depending on what you think the birth date is, and then we'll look at the future. Let's start off with the history section. Let's look back in time. Remember these? Do you remember when a 10 megabyte computer with a full height hard disk could be yours for only $5,995? That's 10 megabytes in something that if you dropped it would land on your foot and break it. As opposed to today, you can drop a terabyte on your foot in the form of a flash disk and probably you'll only end up with a light bruise. Remember the Apple ProRes QuickTime Decoder 1.0? Remember the Quantel Harry? Remember 8¼ floppy disks, 360 kilobytes of information on one simple magnetic media, and it didn't matter how many times you folded it, you still couldn't get it to work in a 3.5-inch disk slot. So that's a bit of history, but what's interesting about those is that all of them had these tightly coupled design compromises to make media work in the systems of that era. And those compromises that were made all the way back in the 1980s are still with us today. We're still battling with some of those compromises that underpin the file formats that we use today. So let's have a look at some of those. Let's kind of go in chronological order. So the first sorts of media files that we could store were pretty much the captioning content. You could just about get the data rate of an RS-422 interface onto an 8¼ disk. You could definitely get it onto a 3.5-inch disk. And anybody who has worked with European captions knows that the famous STL file format, the business-to-business format that allows you to interchange captions for player with other Europeans, has within it a couple of data fields, which is the total number of 3.5-inch disks that your caption file spans, as well as the disk sequence number to make certain that you didn't get your floppy disks out of order. Still in the spec, still used to get those numbers wrong, and you will invoke bits of code that probably haven't seen the light of day since 1999, but could still cause your broadcast player to lose captions. Moving forwards, we started to put audio onto hard disks. Remember the RMO3, those of you who had to work with DEC equipment, maybe the old PDP-8s or even PDP-11s? Those great big huge platters of disk could hold 67 megabytes and sustain, I mean truly sustain, 1.2 megabits a second, maybe megabytes a second, with a 35 millisecond seek time, which meant you could just about get audio out of it continuously, and if you were very careful, you could probably get a sequence of animated stills, which would approximate to video. So 10 megabyte hard disk drives could just about do audio. CPUs could just about do audio, but we're in the era of big endian versus little endian architectures. Basically, if you disrupted the CPU too much, you would get audio stutter, or those animations that you were trying to play back and call video would stutter and fail. Cross-platform code was being developed. Object-oriented development was taking place. But really, if you wanted to get video to work properly, you were talking about customized hardware like that in the bottom right-hand corner, where the format that you had on the platter of the disk was optimized to go through the specific channels of your custom hardware to get the SD out onto the TV screen. It really was a truly proprietary end-to-end system, where in order to compromise for the limitations of your CPU and hardware, you had exotic formats and exotic disk reading software to get that data off the platter. Moving forwards 5 or 6 years, we started to get RAID. We started to get people who were able to put together the inexpensive disks that were being used in personal computers, forming reasonably sophisticated storage systems, where the IPR for media systems was really all about how would you build a media RAID. In other words, one that was optimized for getting digital media on and off those platters. No one disk platter was capable of giving you good sustained SD performance, standard definition performance, but if you put enough of them together, you could actually start to get a reliable, possibly even multi-channel video system built. And you may remember things like the Sprint, the DVS Pronto Store, and Pinnacle were all kind of fundamental founders of these new RAID systems. Even Omnion was their first product was fundamentally how to manage the disks to get the bandwidth required to get multiple SDs off that redundant array of inexpensive disks. And the file formats on the surface of the disk were often proprietary, and the interfaces to them, or the gateways, were also proprietary. And very often what we saw as a file format, an interchange format, was often the proprietary FTP or FireWire or whatever interchange gateway we had to those server systems. And the legacy of those days, again, is still with us today. Meanwhile, in the prosumer world, Apple and Microsoft were slugging it out, trying to get prosumer video with proprietary compression systems within QuickTime, Intel's Indio video system, the initial Microsoft Windows codecs. All of these things were battling for supremacy to try and be the format that games developers and others were using in the consumer industry. Adobe had their flash in the pan. That was a joke. Everyone trying to get the killer app that would give you consumer media at a reasonable price. About the same sort of time, streaming was kicking off, and we were trying to stream video using the RTP system, real-time protocol, and that's still with us today. Simultaneously, we were getting new sorts of viruses and security issues, and suddenly nobody wanted to open up all of their firewall ports to let all of those nasty viruses in. So things like RTP were almost stillborn because the security issues of the time prevented anything going in and out of the servers unless you were going to be doing something like HTTP. The legacy of those systems, again, is still with us today. By the time we got to the 2000s, we had hope. CPUs were fast enough, disks were big enough, memory was cheap enough. The ProMPEG group began a study trying to figure out what was the business problem we were trying to solve by moving files backwards and forwards. More of that later. Would it be possible to make a single, simple, free, easy-to-understand file format that everybody could use? IT companies were busy trying to fix prosumer applications, and Final Cut Pro 7 was set to rule the world. So pretty much by the 2000s, the whole IT media thing was looking pretty good. But then we must remember that no one new format has truly killed all the old formats. Recorded media didn't kill TV, TV didn't kill cinema, cinema didn't kill radio, radio didn't kill newspapers. How many of those formats that we thought were going to die in the early 2000s are actually dead? The STL captions, AES audio, GXF, LXF, MXF, were they still born? Were they going to die? Were they going to live? The reality is that when you invent a media format, That format, even if you try your hardest to keep it within a closed facility or a closed environment, it will leak out. The nature of media is that we share it, we interoperate it, we move it from where it was originated and send it somewhere else so that we can generate revenue. If we're going to make money out of media, then it's very likely that your proprietary media format, even if you try and keep it in a box, will leak out. It's economically in your interests to do so. So a lot of the proprietary formats we thought we were going to die aren't still alive in archives. They're still alive in archives and they're still in use. And one of the golden rules I tell people is that you have to remember that the standards which try and cover a large number of applications are sophisticated. If you sum the total number of pages in any given standard, and then sum the total number of standards that you need to implement for any given application, we're talking over 10,000 pages of specification. 10,000 pages of specification that some engineer has to read and type in so that their C++ code reliably recreates what the standards inventors thought should be put on those pages. So even if the standard is perfect, you have hundreds of implementers all trying to interpret those pages identically. Obviously, you're going to have interoperability standards. Obviously, it's easier for you as a manufacturer to invent something that you own rather than implement a standard. And this leads us to one of the conundrums. It may feel easier for a manufacturer to do their own thing and ignore the world. However, for the industry as a whole, it's actually economic for us to have a standard that we can all interchange. And that's the interoperability dilemma. End users want to exercise choice. They want the right to use the correct codec for the correct application. They want to have big files when quality matters. They want small files when space matters. They want to have any resolution. But what price all of this flexibility if you want a cheap, generic, standard product? The price point of a node of transcode is somewhere between $1,000 and $5,000 nowadays. Maybe as much as $10,000, maybe as low as free. However, if you were to take all the various video formats that most of the transcoders can input or output, and take all the audio formats, and take all the different wrappers, and you put one single test clip in that's 90 seconds long, 90, sort of a minute and a half, a sort of short Lady Gaga song, you make all the possible outputs. Then for every one of the possible outputs, you put it back into the transcoder and make all the possible outputs again to make certain that everything you can make, you can read. For one single clip, how long is that going to take you to do if you do it linearly? Well, even with the best transcoder in the world, it's going to take you about 50 years to do that clip. And every year that passes with each new format, that test time gets longer. But that's not all. You don't just have one video resolution and one setup of audio channels. If you multiply by the number of different video formats and the potential commonly used audio layouts, it might take you a little over 1,800 years to fully test your product. And what does that mean? That means that every multi-format product on the marketplace is by design broken because nobody can fully, exhaustively test their product. It's just not possible. And the more formats we use, and the more we choose to have variants of those formats, the worse the testing problem becomes. So that's interesting, especially as we're looking into the future to figure out how we're going to bring high dynamic range, ultra-high definition, maybe 2K, 4K, 8K, wide color gamut, and multiple interesting frame rates into the scenario. Remember, when people design a facility that uses manufacturers' products, you're designing for change. 8 years ago, today's display devices didn't exist. You couldn't buy a 4K screen for any reasonable amount of money 8 years ago. The heavy lifting file formats did not exist. We had dCinema, we didn't have IMF 8 years ago. Servers running transcode farms the way they do today, they really didn't exist. Today's cloud-based servers, you couldn't get them for that kind of money. A typical 2011 central storage system was far too expensive 8 years ago. And you look at a central storage system that you might build today out of commodity stuff, 8 years ago, it was just not viable. Yet we're expected to design systems and facilities that have maybe a 5 to 10 year life cycle. Even if you're starting to use cloud services, you can't afford to change your fundamental architecture every year. You're expected for that fundamental architecture to last maybe 3 years. It might be a faster turnaround cycle, maybe not as long as 10, but you're still sticking with fundamental architectures for a number of years. Archive ingest systems were expected to be finished by now. We still have a lot of people ingesting content today, so how do you design for change? And this is one of the areas where a fundamental shift took place, maybe 4, maybe 5 years ago, that the underlying file formats are by and large good enough. The interoperability problems don't stem from the fact that the file formats lack features, they stem from the fact that manufacturers and systems specifiers interpret those features differently. So if we want the features to be determined and defined and implemented the same way, we need to know what application we're going to be using. And by application, I mean, are we doing a sports ingest? Are we doing editing? Are we interchanging finished content? Are we creating a service master from which those finished content masters are going to be created? Are we doing HLS streaming or smooth streaming or some adapted bitrate streaming? Each one of those is a different business application that has a different technical solution. And with application specs, you constrain the different options that are required in those different file formats, and you stand a good chance of controlling interoperability, metadata, and costs. Without an application spec, it's a bit like the Wild West. You have to do an awful lot of testing, and even then, you have no guarantee that things are going to ultimately work. So let's have a look at some of the individual file formats that exist, and let's have a look and see how they came about and what those implications are as we start going into the future. Let's start with audio files. Let's start perhaps with the granddaddy, or maybe the grandmummy of them all, IFF, the interchange file format. It was introduced by Electronic Arts over 30 years ago. In 1985, they wanted a way of distributing programs, not media, but fundamental programs that would work on both Commodore and Amiga. The Commodore and the Amiga had pretty much the same hardware, the same processors, the same sort of memory layouts. And so they had this idea of making a file format inside which you could describe the different resources. Here's a bitmap, here's a bit of data, here's a string lookup table, here's some executable code. Here's some executable code that only works on the Commodore. Here's some executable code that only works on the Amiga. So by tagging all of these different chunks, they had a way in which you could have an interchange file format that could work on 2 different platforms, and you could distribute one executable and make more money for less effort. Woohoo! We all like the sound of that. This is where the 4CC codes come from. The 4-character code was essentially the identifier on those chunks. So group chunks like form, list, and cat still exist. And we'll talk more about chunks a little bit later. So IFF kind of kicked it all off. Fast forward 2 or 3 years, and we end up with 2 different fundamental media types. We have the AIFF, the Apple IFF, and RIFF, or RIF, the Resource Interchange File Format. What's the difference? Well, pretty much they were the same as each other, except because at that time, Apple was using Motorola chips, which were big endian. AIFF was the big endian variant. And Microsoft and IBM were using Intel chips, which were little endian. We had the little endian format. In other words, if you had a 2-byte audio sample, with AIFF, you send the most significant byte first and the least significant byte second. RIFF, you do it the other way round. To make things even more interesting, the WAV variant of RIF for CD bit streams was at 44.1 kilohertz for very good reason, but not one that you'd ever want to repeat again. Despite the fact that most broadcasting was at 32 or 48, 44.1 was the predominant sampling frequency for audio for a very long time. The EBU extended the WAV format to have some of these extra chunks that describe things that you need if you're going to be doing broadcasting. So broadcast WAV, or BWAV, is essentially just a WAV file with extra chunks. Those extra chunks have different 4CC codes to identify those extra chunks, and we end up with BWAV. An application that expects BWAV but gets WAV may fail because it doesn't find those extra chunks. As soon as we started doing very big files and we needed 64-bit addressing, we discovered that the original IFF, for whom 32-bit address space seemed like it would last forever, we discovered it wasn't enough for modern big audio files. So RF64 is essentially a 64-bit variant of our good old favorite IFF format, extended with chunks to become BWAV. As you start to add surround sound, streams, object-oriented sound, and all that kind of stuff, we can still extend BWAV to have extra chunks. What's interesting, though, is we start with a consumer format, and it trickles downstream, it leaches upstream to become a professional format, or we start with professional formats and they trickle downstream to become consumer formats. By and large, most of the formats that were invented in the 90s didn't stay where they were invented. They either trickled upstream or downstream according to different applications that people wanted to do. But those aren't the only audio file formats. No, there's loads of them. They were invented for specific applications. And as I've said earlier, even though you think you've got a format that's going to stay in its application and not leach anywhere else, it never happens. So the 3GPP format, which is a variant of the MP4 format, you think it's going to stay just in the 3G mobile networks? No. It ends up in broadcast space because people use mobile phones to record audio clips for the news. So whatever format you invent, it will leak, it will migrate, it will move. This is one of the big lessons from history, that if you forget everything else I say today, and you wonder what that noise from my laptop is in the background, if you forget all of that, just remember, any file format you invent, proprietary or standardized, will move. It will find new applications, and you cannot control them. It's as simple as that. So we have lots of audio file formats that move around the world. But let's not forget the world of free. A lot of the file formats are free. There's a lot of free tools out there, free audio tools that do free stuff. And if you're a production company, you're strapped for cash, it's always very tempting to use the free tools because they work for you. You don't care that you're using OGG or some random audio format that your end distributor is unable to handle. All you're concerned about is reducing your costs to make some fantastic content. And that's great, until you start using specialist tools and plugins in your free tools. It then becomes very, very hard to archive what you're doing. How do you remember how you got those particular effects if they're done on a non-supported, non-standard editing platform? Well, the only way to do that is to archive the application as well as to archive the project. Maybe if your production's not worth very much, you don't care. But for some of the bigger productions, you really do. So once you start to archive these free tools, it suddenly becomes very difficult to remember what it is that you did. Because often the only definitions of the plugins for the free tools, not the free tools themselves, they're often very well documented, but the documentation for the plugins is often non-existent. It just does what it does because somebody had a clever idea. So you have to archive the plugin and hope you can still run it in 10 years' time when we're up to Windows 20 or Apple OS XX or whatever it is that you were running your plugin on. What about video files? Really, there aren't many video-only file formats. What we think of as video file formats are very often wrapper file formats, because most media files that we use that we think of as video actually have interleaved audio and video. So really, you probably only have .gif, animated GIFs, .pngs, animated. M2V or M4V files, those are pretty much the only video-only files that really you see in volume. All the rest are wrapper files. So let's have a look at wrappers, because really that's what we're talking about. There are a lot of wrappers, many of them in the consumer space or the prosumer space. A lot of them were because a particular device became very popular, and its own proprietary format generated a lot of files, and lots of tools were created to support that popular device. Whether it's a creative audio device, or whether it's a QuickTime-oriented device, or whether it's MP4, whether it's a serialized transport stream because that was the easy way of capturing off-air video, or whether it's serialized something else that people found a way of doing. A lot of these consumer file formats really don't have the documentation you need if you're going to build an archive or you're going to build a business around those file formats. If your business is predominantly around editing, you really want to optimize the file format you're going to use for editing. AVI, MOV, MXF, all file formats around which editing tools have been designed and built. Some of them have advantages, like MXF was designed for growing files, AVI was designed to wrap a whole variety of different codecs, and MOV was really almost vertically designed for the Apple environment. So Apple plus ProRes plus .mov gives you good reliability because essentially you're only using one library, and that one library was used to build all the apps. In a way, you've bypassed the interoperability problem by choosing one vertically integrated solution, which is great if that's what you want to bet your business on. And many people have, and many people have done it successfully. The wrappers that we use often hide the codec support issues, specifically how we handle timecode, offset, synchronization, intra and long GOP, clean start, fast starts, and handles. In other words, even if you have a completely vertical Apple plus MOV solution, you can still run into problems with things like timecode, because people building applications have to handle the timecodes correctly. More of that later. When you're buying or selling a camera, you often optimize the file format that the camera produces to show off the features of your camera. And we see that there are lots of MXF variants which have been created to show off various features of different manufacturers' cameras, and with good reason, because cameras are intended to do funky stuff. When you press the record button, you cannot write into the camera what the duration of that file is going to be, because you don't know until you press the record button at the other end. So these open-ended behaviors of cameras lead to interesting speciality variants of .mov, .mp4, sometimes .pairs, MXF, MTS, and a whole variety of other formats. And very often the software that you put in is matched to the sensor. So even if you have a standardized file format, the underlying codec might be a bit weird. A lot of file formats were spawned in the media industry around servers for reasons that I've explained earlier, because the hardware meant that you had to match the file format to the hardware in order for the thing to work all the way through from the 80s to about the middle 2000s. So as a result, a lot of code and a lot of hardware exists, and we're still living with a lot of that legacy to this very day. So even though the fact that all the big names can stream directly from some arbitrary NAS or cloud storage, you still find that a lot of the behaviors and the underlying code paths still have code chains that go all the way back to that customized hardware, because you have to have backwards compatibility in this industry. If you could play out a particular file in 1999, you still want to be able to play out that same file in 2009, and probably still in 2019. Mezzanine files is the name of the file format that you use in your facility. You bring all the files in, you normalize them to your mezzanine file format, and then you send them out in a different format. Originally, this was the Wild West. Everybody chose their own particular favorite of MXF or MP4 or QuickTime. Ultimately, it's boiled down to MXF or QuickTime, based around either a J2K, an AVC, not any HEVCs yet because it's still a bit pricey, but really everything's boiled down to these major formats. And mostly that's down to cost. Once the interoperability issues are fixed, it makes a lot of sense to try and commoditize the hardware and the transcode software and the I/O software that you're using. However, we're starting to move out of that stable environment into a more random environment. As IP transport starts to show its face, we're starting to see new breeds of link codecs like Dirac and Tico and lightweight J2K and others. If it exists on a wire and it's going over IP and being handled by a CPU, you can bet your money that somebody's going to dump it onto a file and call it a .mxf, whether they bother to go through the standardization process or not. Someone's going to use the QuickTime format and dump it into a QuickTime. Somebody's going to go and use AVI synth to dump it into AVI. There'll be riff headers. There'll be new 4cc chunks. It will happen. A lot of these new developments are being done quickly. Will people bother to go through a due process standardization process to get these file formats standardized? I don't think so. So we've gone from the Wild West to a period of relative stability into this new era as we're going into IP and ultra-high definition, where actually some of that good standardization and sensibilization work is being undone. The application specs don't exist because we don't quite know what the applications are yet. I said I'd come back to Timecode, and I have to mention Timecode because the people who build the products tend to be young software engineers who don't know all of the glorious history that we have lived through. We need Timecode today. Although SMPTE has defined a time label system and a PTP synchronization system that will eventually be much easier and more straightforward to use, Timecode isn't going to die out. It's still going to be around a decade from now. You need it to align independent devices, be they audio or video recorders. You need it to align assets if it's a separate caption file to a video file that you've got. You need it to get those edit points correct when you're interchanging EDLs or BXF files between systems, and you need it to accurately count durations. And the reason it's difficult, particularly when people are writing software for the American zone, particularly when those software engineers have computer backgrounds and not media backgrounds, is understanding the number 29.97. Yes, okay, black and white TV was 30 frames per second, and there was a choice about what you're going to move to bring in color so that you didn't disturb the audio and you didn't disturb the chroma subcarrier and you didn't have to do anything particularly nasty. To make it all work, the decision was taken to move the horizontal line rate by a factor of 1,000 over 1,001. Unfortunately, this is often written as the number 29.97, but really it's not 29.97. It is truly 1,000 over 1,001 multiplied by 30. It's that fraction. I've seen code when I've been trying to debug synchronization problems between people interchanging MXF files, where the problem came down to the fact that the person who wrote the code typed the number 29.97 into their frame rate. And so over long periods of time, 29.97 is not the same as 30 times 1,000 over 1,001, and you get drift, and you get sync, and you get audio dropouts. It's a backwards compatible solution to make everything work, but we're entering an era where the grey hairs like myself, who understand the reasons behind this stuff, are not allowed to write code anymore because they're too old, and the young, really bright kids who write the code don't understand the background. Because of the difference in frame rates, we have the perception that drop frame is about fractional frame rates and non-drop frame is about non-fractional frame rates. This is not the case. Timecode drop frame and non-drop frame are just counting modes. And my good friend John Pallett and I came up with these slides that we helped people understand the difference between the counting modes and not the frame rates. On the left, we have a non-drop frame counting mode, NDF. It has a full colon. Get it right, everything's good. On the right, we have the drop frame mode, which has the semicolon. Get it right, everything's good. Get it wrong, and, well, bad stuff drops on the floor. If you can't remember that, Here's a visual diagram, and I do hope you're not eating while you're watching this. So on the left, we have a full colon. Everything falls straight through. On the right, we have a semicolon. This is drop frame. Get the semicolon wrong, and, well, bad stuff's going to fall on the floor. You will never forget drop frame again and your semicolons. But it's just a counting mode. It's like leap years. You count 30 for every second. If you count 30 for every second, you'll be off by 108 frames per hour if your actual frame rate is 30 times 1,000 over 1,001. You can be off by 2 minutes a day. Congress wouldn't change the rotation of the Earth or change the duration of a minute, so we had to do something different. So Cincy came up with a counting mode that's a bit like leap years. Now, we had a leap year this year. Nobody had a problem with inserting an extra day. We didn't spin the Earth round an extra time. We just counted differently this year. We just decided we were going to have a February the 29th, and that's just fine. So you have to remember that drop frame is just a counting mode. And because somebody has counted with drop frame doesn't mean that the underlying frame rate is actually 29.97. They could have got it wrong. And just because somebody's counting at 30 non-drop frame doesn't mean that the underlying frame rate is actually 30. They could have got it wrong. And very often file format interoperability comes from the fact that people made an operational mistake. And that operational mistake has been technically followed through the entire chain to mix NDF and DF timecode counting modes with 2997 and 30 frame rates. And this is exemplified in one of the projects that I worked on, which is the I don't know what I have problem. Imagine a world where you've got captions that were QC'd and manually aligned, so you had humans to fix stuff up. You start to digitize the archive. Some caption originals were 2398, were 2997, or maybe 30. Some were aligned to the first frame of clock, first frame, and some were aligned to the start of clock. Some were maybe aligned to the phases of the moon, who knows? But none of that metadata was captured. And so when you try to automatically digitize that, you're basically dropping money down a black hole. Just because technically your file format handles drop frame, non-drop frame, and multiple frame rates doesn't mean that operationally all your files will comply. We don't have the metadata richness in our world to ensure that at the moment. This is one of the things we've learned from history. Creating the metadata and using it well are completely different things. And caption files are a great example of that. Caption files are notoriously difficult to use because they lack a lot of metadata. 1927, we had the first audio movie. In 1947, we had the first captioned movie. It wasn't until the early 1970s that we had television subtitles and captions appear. And you look through this history of standards, and what's interesting about it? Well, actually, nearly all of these standards are transmission formats. It's probably only STL and the TT, the time text ones, which are actually business-to-business formats. And this means that when you're trying to obey the law, and remember, you can put out black and silence in most territories around the world, but unless you caption that black and silence, you may go to prison. It's very hard to build a proper anything-to-anything workflow where you've got captions. Because if you take all the possible inputs and all the possible outputs of all the files that you'll see going around your facility, you have to multiply the test cases by the number of inputs and outputs. So with 15 inputs and 22 outputs, that's 330 test cases times the display modes for each standard gives you 1,000 different test modes just to test your captions in a facility. That's never going to work. So to do it properly, you probably need to have a caption mezzanine in the middle. And really, there's only one caption mezzanine that really exists today, and that's the TTML format. It ain't perfect, but it's probably the only caption mezzanine that we have. So if you're truly going to build a compliant caption, subtitle, aware, anything-to-anything workflow, and you don't have TTML anywhere, well, good luck to you is all I can say. And that lack of standards means that most workflows today, and here's one from the Dalet Academy Workflow Controller, probably means that you have to build a caption workflow that has these magic external tools in the middle to make your stuff magically work. Because really, the only way you're going to get it to work today is with some sophisticated TTML processing. So happy 10th birthday, MXF. I put forward an idea for MXF back in 1997, but the UK government rejected it because there was no problem. It had already been solved. And Joe Zalla wanted to call it M&M, not MXF, because M&M was a rapper. Yeah, thank you, Joe. And the problem that we were trying to solve, as I already mentioned, is that there's too many formats and too many vendors, and all the time all the vendors do all the formats, and we pass that cost on to the user community. And passing that cost on to the user community means it costs more money than it should. And we can't standardize the video and audio codecs because those depend on the applications, but we can standardize the wrapper, and that's where MXF was meant to step in. So I asked last year for MXF's 10th anniversary for a presentation I did in Japan, what did the world think about MXF today? In Japan, the ARRIVE, the standards body in Japan, was really quite happy about MXF because very early on, they built ARRIVE standards around MXF for interchange within Japan. So essentially a Japanese application programming interface. Fantastic. I asked AdID in America, what's stopping MXF from penetrating the advertising industry? Why is it still ProRes and QuickTime? Well, really, it comes down to the fact that that's what everybody's always used, and that MXF doesn't currently give any benefits because nobody has sorted out the metadata problems of advertising with an MXF container. Shouldn't be difficult to do. No one's focused on it. I asked Adobe. Adobe had lots of good things to say about MXF because it has essentially stabilized and made the marketplace more controlled and more accessible. So Adobe see MXF as a good thing. I asked AMWA. AMWA, the Advanced Media Workflow Association, were predominantly involved in pushing forward the application specifications and getting them into the industry. AMWA are very keen on MXF, very keen on application specifications, and don't really care whether it's MXF or ProRes or QuickTime or anything, as long as there's enough people who agree what that application is and enough minds go together to collaboratively create a specification based on open standards to solve that particular business problem. I asked Archimedia, who build a conformance and compliance player, what they thought about MXF, and they were genuinely positive because most of their customers are using MXF for most of their playbacks in most of the applications. So it seems that MXF is doing quite well there. The digital cinema guys are obviously very, very biased towards MXF because digital cinema really is an MXF distribution format, and there have been no dark screens despite there being about 150,000 movies in 140,000 cinemas showing over 1 billion showings of MXF and carrying billions of dollars of revenue every year to the eyeballs of the viewing public. The application specification that is the digital cinema standard has been very reliable and very secure. In fact, sometimes I wish with all of those billions of dollars flowing through that I've found a way to charge just 1/1,000,000 of a cent for every MXF file. Never mind. The Digital Production Partnership, too, has created an application specification for the UK. And if you're going to NAB, go to the DPP NABA, North American Broadcasters Association, launch of the application specification for the USA. Really important groundbreaking news. An application specification for the interchange of content in the US. Big news. EVS, who bought OpenCube, have moved from being a software vendor to an applications vendor because really MXF is just a tool that solves the application interchange problem. So it's interesting to see that the MXF community, the tool building community, has really turned into an application creation community. Grass Valley told me that MXF is still the Wild West of media formats. There are no laws, there's too much choice, playout servers have to validate too many flavors of MXF, and that many people, I think that means Grass Valley or maybe Grass Valley customers, think that constrained MXF flavors mean that MXF is a failure. Well, that could be taken as a truism. The same issue is also occurring with BXF. The trouble is, as I explained earlier, people like to have stuff cheap and quick. And, well, we'll figure out the future when the future comes along. MOG was another one of the early MXF technology vendors who ended up building applications. Again, they've gone from a situation where instead of building MXF tools, they're building applications with MXF, because really, it's all about the application. And MOG has been one of the great companies, that, along with OpenCube, that's really helped to stabilize the MXF ecosystem. But really, the big names like Panasonic and Sony have done a lot to stabilize the system by having constrained formats coming out of their cameras, constrained and consistent formats coming out of their cameras. So Panasonic have built an ecosystem based around what comes out of their cameras, and Sony likewise have built an ecosystem that's based on what comes out of their cameras. And those ecosystems in turn have generated a lot of facilities that basically take an MXF in one variety, spin it around, and turn it into MXF of another variety. Telestream said that growing file support within MXF was a huge advancement. And despite the first few years of MXF being the different flavors, the Wild West, and chasing all of that, that actually we've come to a good place. The MXF variants have become neutral and become a common ground for interchange. So by and large, this is a good thing. And year on year, we see more and more people adopting MXF and using MXF as the interchange format. So really, the world's come down to MXF and QuickTime nowadays. So what about my wishes for the future? That was a view through history, but actually I think I've highlighted quite a few things that went wrong with the past. And so it just remains for me to sum up now by talking about the future. So here are my big wishes for, actually those are my other wishes for the future. Yes, riding a bike with Laura Trott. Let me just clear my browsing history and move on to the next slide. There we go, that's much better. So what are my wishes for the file format future? My wishes are that people designing systems and facilities consider the total cost of ownership of the file format and not just the capital cost of putting some free tools in today that cost more money downstream than they saved upstream. I wish that whole ecosystem was familiar to people at the point of design and the point of committing. Very often, the people who have commissioned these systems don't understand the downstream costs that are implicit in going for the short-term cheapness. My second wish is that implementers would consider interoperability right from day one. Even if you're going for a single vendor system, the cost of bringing in foreign material from that single vendor system can be expensive if you don't consider the interoperability issues. We've learned from history that no system remains single vendor enclosed ever. Eventually, it will leak. Also, I wish for better collaboration at a commercially significant scale. So application specifications that really mean something would make a huge difference, not just to the vendors and users, but would make a big difference to our industry. And I'm wishing you all a very well-formatted, file-based future. And I thank you all very much for listening. And if you remember one thing from this webinar, one thing from my long talk, it's all about the cost of special. It costs a lot to be special.